Hello, and welcome to another video from the University of Florida's Scan Lab. My name is William Mitchell, and this video is going to be an introduction to optical transceivers. The material in this video is a collaboration of Litin Kumar Biswas, Himanandahan Reddy Couture, Patrick Craig, and Pavan Babu Arjuna Mahanti, all under the supervision of Dr. Rain Gan Matlag and Dr. Naveed Asadi. If you're not already familiar with photonics, I suggest you go check out one of our other videos available on the channel before you start exploring optical transceivers. This photo is a great representation of a system that integrates optical transceivers with electronics, and is one that we'll return to again at the end of the video. The goal is to be able to understand how some of these components function, the challenges associated with realizing them, and how they work together to make photonics such a powerful technique. After we cover the background and purpose of optical transceivers, we'll touch on how they integrate into these systems with things like optical connectors, single-mode fibers, and optical tiles. We will begin with a brief introduction to silicon photonics and how it relates to transceivers, then talk about the basic principles of optical transceivers. We'll move on to discuss the technological impacts of optical transceivers and what applications they're used for, then dive deeper into the basic principles of fiber optic interconnects. Next, we'll define what alignment means for optical devices and go over some advanced alignment techniques. And finally, we'll talk about some advanced interconnect methods and address some challenges and potential solutions for optical transceivers. Transceivers are devices that can both transmit and receive signals and are essential for managing data transmission protocols. They're typically small packages containing a transmitter and a receiver, and then some connection to a local logic device. Now, traditional transceivers are electron-based and rely on electrons traveling through copper pathways to transmit data. They can offer decent bandwidth and relatively low power consumption, but significantly struggle with long-distance transmission. For short consumer applications like Ethernet, electrical cables work just fine. But for industrial needs, such as data centers, AI workstations, and telecommunications, higher bandwidth and lower energy consumption are crucial. And this is where photonics can offer a solution. We can transmit data with light through fiber optic cables at the speed of light to enable faster speeds and consume less energy. Now, however, electron-based logic still dominates when it comes to actually performing computations. So a device that bridges the gap, being the optical transceiver, was invented to facilitate the connection for photonic integrated circuits, or PICs. Now, initially, optical transceivers were these pluggable modules soldered onto a PCB and connected to a server's logic. But advances in photonic integrated circuits now enable these co-packaged solutions, placing transceivers inside logic substrates to maximize performance. Now, placing these transceiver modules as close as possible to logic maximizes the benefits from using photons and is enabling extremely fast data transmission speeds. Now, co-packaged optical solutions exploit silicon photonics on the wafer level to provide the best bandwidth, power efficiency, and latency to support AI and machine learning infrastructures that rely on the highest speed data communication. But whether it's co-packaged or pluggable, all optical transceivers play a key role in optical fiber communication by converting signals between electrical and optical modes. One of the most widely used optical transceivers is the SFP, or Small Form Factor Pluggable, known for its cost efficiency and ease of implementation. As the name suggests, these transceivers have a compact design and allow fiber optic cables to be plugged in, connecting to larger server systems. They can be conveniently hot swapped as needed and provide a great amount of versatility for industrial or home-based server systems. Now, the working principle of transceivers is really quite simple when you zoom out. These electrical signals, as a series of ones and zeros from one logic device, gets converted into an optical signal by the SFP so it can cover a long distance at a really fast speed, where it then gets converted back into an electronic signal at the other device's SFP transceiver. In general, this allows the two devices to communicate across vast distances. And if we zoom back in a bit and look at a single optical transceiver, they use a light-emitting diode to talk, or generate the photons, and a photodiode to listen or detect the photons. And while these functions themselves are pretty easy to understand, the actual design of these components can get quite complicated. The transmitter must be paired with an active modulator so that it can properly encode the information into the outgoing optical signal. And the photodiode, acting as the detector, has to receive those encoded photons and decode them back into an electrical signal. Then, that signal has to be passed through a preamplifier so that it can be easily read by the next logic device. Here's a much more detailed diagram of the inner workings of an optical transceiver. A core component is the microcontroller, which must communicate electrically with the transmitter to drive the light source. This component also controls the modulation of the photons being emitted from the transmitter. And after they're modulated, they have to be coupled into a fiber array so that they can travel to their destination. And on the receiving end, the fiber array has to be coupled back to the photodiode. Now, most of these components are active, but it is important to note that things like waveguides, gratings, couplers, and splitters are all passive photonics components that cannot be adjusted as easily since they're actually part of the structural design of the device. The demand for fiber optic technology has significantly increased over the past several years, and it's all directly enabled by optical transceivers. And that's because applications can be found wherever high bandwidth data communication is needed, being services we interact with often, like fiber optic internet, cloud computing, and entertainment media. But the demand for optical transceivers is especially being driven by an increase in deployed AI clusters like ChatGPT and telecom providers that are upgrading their servers to prepare for 6G technology. Out of the predicted sales for a high-speed interconnects manufacturer like Light Counting, optical interconnects like transceivers are predicted to grow within the industry, along with other devices that are typically paired with them, such as Ethernet switches, routers, firewalls, network interface cards, and fiber converters. Now, connections between servers and switches in data centers require the use of optical modules, and base stations rely on optical transceivers to send and receive signals. In addition, 5G networks that provide for highly populated areas depend on the transceiver to support the heavy traffic and are a big reason that this technology is receiving so much attention. These devices are necessary in all types of telecommunication applications, which in general are seeing rapid growth as data becomes more and more important. Small form factor pluggable transceivers have widespread adoption as a cost-effective solution because they have a basic form factor and can support data transfer rates up to a few gigabytes per second. Now, the transmitting and receiving elements can either be designed unidirectionally with separate transmitting and receiving channels, or bidirectionally with transmitting and receiving functions merged into the same channel. Now, transmitters are known as the Transmit Optical Subassembly, or TOSA, and are always responsible for generating photons with the encoded information from the electronic signal. Now, the receiver is known as the Receiver Optical Subassembly, or ROSA, and is always responsible for receiving the encoded photons and converting them back into encoded electrical signals. Now, these assemblies work together with the microcontroller unit to provide the talking and listening functions of the transceiver. And in a unidirectional design, they have their own separate channels. Now, the PCB's housing protects the entire device and defines the form factor of the product, and the pluggable pins on either end enable hot swapping, so the transceiver can be modded anywhere onto a server system. Now, additionally, there are heat spreaders that are mounted across the assembly near key components like the laser driver to draw away heat and give the device a boost in efficiency. Now, a bidirectional optical subassembly, or BOSA, is generally the same as a unidirectional assembly, but the key difference is that the TOSA and ROSA are merged. The main advantage of BOSA is its integrated nature, allowing the overall size to be reduced and only a single optical port to be used. Additionally, BOSA assemblies enable wavelength division multiplexing, or in other words, the ability to simultaneously transmit multiple different data streams through the same fiber at different wavelengths of light. You can imagine turning a 2-lane highway into an 8-lane freeway without expanding the road at all. Now, WDM effectively multiplies the bandwidth capacity of existing fiber infrastructure without requiring additional cables or active components. And when choosing a suitable SFP module, It's important to consider many factors, like the data transmission rate, maximum range, size, power efficiency, and number of channels. Transceivers are most often evaluated by the speed that they can transfer data, but they can also be classified into other categories like form factor, package type, what industry standard they follow, and how many channels they have. Now, one of the first standard optical transceivers ever mass-produced was the Gigabit Interface Converter, or GBIC, in 1995, and it was capable of a data transfer rate of about 1 gigabyte per second. Now, 5 years later, the first ever SFP was released, enabling speeds up to a few gigabytes per second using a single optical line. SFP Plus is an enhanced version of SFP that boosted speeds up to about 10 gigabytes per second, and SFP 28 is an enhanced version that keeps the same form factor but allows speeds up to about 25 gigabytes per second. And around the time of SFP 28 came the QSFP Plus, or Quad SFP, which was used 4 optical lanes capable of 10 gigabytes each to push speeds up to about 40 gigabytes per second total. Now, in the early 2020s, there are plenty of options to match all data transmission needs at varying costs, maxing out at speeds of about 1600 gigabytes per second. These extremely high-speed devices, like SFP-DD, use double density designs, where there are 2 BOSAs instead of only 1, increasing the bandwidth while maintaining the form factor. Now, GBIC, XFP, and CFP are generally outdated form factors that are much less common, and that's because most users have adopted the SFP core. Now, choosing the correct transceiver for your application all depends on the capabilities that you require. In general, most transceivers are some form of small form factor pluggable, even if they do use a co-packaged design. And the common vendors that are manufacturing transceivers includes Intel, Cisco, and Dell for applications like data centers and data networking. Now, some applications are so widespread and generic that you can find the same spec device being sold by multiple different vendors. And to help standardize the market, a variety of physical layer standards, or industry standards, have been defined to classify transceivers for different operating conditions and applications. These transceivers that are sorted by applications are usually by long-range transmission or short-range transmission with extremely high speed. But the most commonly factor that differentiates these optical transceivers is their maximum data transfer speed. So why should you learn about optical transceivers? For one, they're a big reason that we don't have dial-up internet anymore, and why we're able to do things like stream 4K movies and participate in video conferences. In modern data centers, optical transceivers can become a huge bottleneck because they need to convert enormous amounts of data between electrical and optical signals at increasingly higher speeds and growing volumes. And while fiber optic cables can theoretically carry massive amounts of data, the transceiver's ability to process and convert these signals fast enough is a crucial limiting factor. These devices form the backbone of modern communication, powering everything from network switches and routers to massive data centers and telecommunications infrastructure. In data centers, optical transceivers are the vital links connecting countless servers and switches through fiber optic cables, enabling cloud services and internet connectivity. In base stations, they facilitate crucial connections between remote radio units and baseband units. And for 5G networks, these modules are especially important for handling both front-haul and mid-haul functions across different network layers to deliver the ultra-fast speeds of 5G. And as these networks expand and data demands grow, particularly in areas like edge computing and Internet of Things deployments, developments in optical transceivers will be crucial for scaling digital infrastructure. While innovating the transceiver design is important for enabling functionality, the testing and validation of optical transceivers is essential to maintaining reliability and performance. Functional reliability tests verify performance metrics to prevent failures in critical applications like communication and sensing. And as modern applications grow and demand more performance and reliability, from things like data centers handling AI cloud services to telecommunications networks supporting essential business, rigorous testing ensures that these components can withstand the real-world operational demands while delivering consistent performance. At the manufacturing level, early defect detection through wafer-level and post-assembly testing helps maintain high production yields while reducing costly failures. and this becomes especially important as optical transceivers continue to shrink in size while increasing in complexity. The testing process must validate not only the individual components, but also their interactions together in hybrid optical electronic systems. As transceiver technology develops and we become more reliant on its infrastructure, testing and validation will only become more important. Specifically, developing efficient electro-optic testing compatible with high-density photonic devices is a critical challenge to solve if we want to fabricate smaller and more advanced designs. Alignment of fiber optic cables and their respective transceiver modules is a crucial element of photonic devices that must be checked for. And if not considered, alignment issues can lead to major inefficiencies or even a complete loss in signal. So it's important to ensure that fiber arrays are oriented directly in front of the PIC's receiving ports and that each optical cable is transmitting to the correct channel. Now, alignment techniques for optical devices as a whole typically belong to one of two categories, being either passive or active. Passive techniques rely on inherent mechanical precision, like how a USB cable slides into a slot and only fits in a specific orientation. These techniques don't provide active feedback, but aim to automatically align components through predetermined mechanical features without active feedback. Active alignment, on the other hand, does provide active feedback and enables much higher precision compared to passive techniques. With active alignment, a computer-controlled precision stage can adjust positioning based off feedback data, and the position can be continuously adjusted until the optical power and coupling efficiency are maximized. One way this is done automatically is by incorporating alignment loops into photonic chips. With alignment loops, the intensity of the optical signal can be measured and monitored as the precise stage makes the fine adjustments to improve it. And when the fiber array is correctly oriented, photons will be redirected from one fiber into another through the alignment loop, allowing the quality of the transmitted signal to be verified by measuring the returning signal. Now, these alignment paths are not functional, so they do end up taking valuable space and can add cost. However, they eliminate the need for probes, which generally require more cost and effort to incorporate into a manufacturing line. Now, alignment loops are just one technique used to evaluate alignment, but they can be especially useful because they provide real-time feedback for precise alignment assembly and testing for PICs. In real-world industry settings, specialized equipment from companies focused on photonics assembly and testing, like Ficontech, are used to achieve extreme precision when aligning optical components. Assembly systems use real-time optical power measurements and precise automated positioning systems to optimize alignment. Alignment tolerance refers to the allowable deviation or error in positioning optical components that maintains an acceptable level of system performance. This means that the fiber orientation has some wiggle room between perfectly aligned and completely misaligned, where the system performance is still acceptable, just not ideal. Now, graph A represents the power penalty for misalignment in the XY directions. Essentially, how the misalignment of the center axis of the fiber optic cable and the center axis of the receiving waveguide affects transmitted power. Now, a displacement of only a few micrometers can cause significant penalties to the amount of transmitted power, negatively affecting whatever the device is. And as this misalignment continues to worsen, the power penalty becomes more and more severe. Graph C shows a similar story, except now the power penalty is plotted against radial misalignment, or how perpendicular the optical fiber is to the receiving waveguide. Again, with a small deviation comes a large power penalty, significantly affecting device performance and efficiency. A major component of increasing the efficiency of optical transceivers is also minimizing the loss among fibers, and especially at the interfaces. One solution that has been developed to mitigate this issue is index matching epoxy, which is a specialized adhesive for optical fibers and waveguides that matches their indexes of refraction so that they appear transparent to the passing signal. Now, this graph shows the optical coupling efficiency plotted against the misalignment of an optical fiber and includes two samples, one with index matching epoxy and the other one without it. We can still determine that misalignment adversely affects the coupling efficiency, but we can also see that the sample with index matching epoxy performed notably better even with some misalignment. Additionally, to improve alignment, polarization controllers can be used to improve the consistency of light traveling through the optical fiber, increasing transmission quality. Polarization control is especially crucial in high-speed optical communications because it helps minimize signal distortion and reduces bit error rates. This becomes particularly important in advanced modulation formats where maintaining signal integrity is critical for achieving those higher data rates. Now, the precise management of light polarization also helps compensate for environmental factors like temperature changes and mechanical stress that can affect fiber performance, ensuring reliable data transmission even under varying conditions. However, when we scale down to chip-level operations, we face additional alignment challenges that require specialized solutions. Photonic integrated circuits that use an array of fibers at the chip scale requires an additional component known as the waveguide array to fiber interposer in order to align respective optical fibers and minimize loss. Now, when waveguides are dense and parallel and straight, like figure A, there's a chance that photons can leak from one waveguide to another and lose their original path. Now, the fraction of light that swaps waveguides can be represented as its coupling factor. And researchers experimenting with meandering waveguides found that this cascaded waveguides assisted with focusing photons so that they exit the same waveguide that they were injected to, resulting in a negative coupling value with equal magnitude. Now you can visualize this with figure C. The main goal is to ensure that a signal injected into a waveguide is emitted out the same waveguide without distortion. If a waveguide starts transmitting at 0, it should also end transmitting at 0 and not be affected by the neighboring waveguides. Now the structure shown in figure E was fabricated to test the efficiency of parallel waveguides versus the cascaded waveguide design. Photons passing from left to right will experience the cascaded waveguide before spreading out and being evaluated by a detector. And photons passing from right to left will experience the parallel waveguide before spreading out and being evaluated by the detector. Now the normalized intensity plots from figure F and G show how noise is eliminated with the cascade waveguide design. When sending only a signal through the center waveguide, the parallel waveguides resulted in a mix of signals, while in contrast, the cascaded waveguide design maintained the signal integrity and only emitted through the center channel. Photonic devices as a whole are known to be complex and really challenging to get just right. And this is mainly because photons are inherently limited by the size of their wavelength, which can make designing dense, miniature structures quite difficult. And fabrication itself is also a challenge, since photonics requires expert precision and cleanliness to consistently realize structures fit for manipulating photons. These structures are fragile and much more susceptible to harsh environmental conditions like thermal and mechanical stresses, and they require a lot of time and energy to ensure that fibers are correctly aligned, transmitting to the correct locations, and maintaining the correct polarization across material interfaces. Now, the silicon industry has a history of turning a once-thought dream from the future into a consumer technology, so all these challenges are being addressed and tackled in research and development. Creative advanced alignment techniques like alignment loops are one example of engineers developing solutions to these challenges. Enhanced materials like index matching epoxy and optimized designs like cascade waveguides are also innovative ways that optical interfaces have been improved upon. New techniques like compensation mechanisms are being developed to mitigate distortions and losses inherent in structural designs, and programming-based solutions like optimization algorithms are being designed to interact with the microcontroller and incorporate artificial intelligence and machine learning to compensate for signal distortions, predict failures, and adapt to varying channel conditions. Now, optical transceivers are pushing the boundaries of what's possible in data communication by balancing physics, engineering, and computation to achieve unmatched performance. The challenges are significant, but the solutions being developed today are enabling faster, more efficient, and reliable global connectivity for the future. I hope this image comes across a little more clear now at the end of the video, and that you're able to somewhat trace the path of a photonic signal on a PCB like the one seen here. These optical tiles are seeing a lot of development and are linked to photonic integrated circuits, which are driving devices towards smaller and smaller footprints. In the next video, we'll cover optical fibers in more depth with multimode and polarization maintaining fibers, how photons are controlled and routed with switch tiles, fiber coupling, and much more. If you would like to explore further on the topics discussed in this video, the sources listed in the bottom right corner of each slide are referenced here.